This is the second model of Chapter 9, Electrons in Atoms and the Periodic Table. By the end of this model, you will be able to understand and explain the key characteristic of the Bohr model of the atom, to understand and explain the key characteristic of the quantum mechanical model of the atom. Also, you will be able to write electron configurations and orbital diagrams for atoms. You will be able to identify valence electrons and core electrons. You will write electron configuration for an element based on its position in the periodic table. You will also recognize that the chemical properties of elements are largely determined by the number of valence electrons they contain. And finally, you will identify and understand periodic trends such as atomic size, ionization energy, and the metallic character. So, neon atoms inside a glass tube absorb electrical energy and then re-emit the energy as a red light. Here we have an example of mercury in the left, this tube with mercury, and they basically emitted blue light, while hydrogen at the right hand here emit a pink light. Okay, so each of this element, they emit a specific wavelength and a specific color. The emission spectra of the elements are not continuous. So for a white light spectrum, the spectrum is continuous, as we saw before, with some radiation emitted at every wavelength. We remember that we have here the red one that is around 700 nanometers, and it goes all the way through the violet that is around 400, but it's continuous. There is no interruption between the wavelength or between the colors. Now, however, for the emission spectrum of individual elements, it includes only certain specific wavelength. For example, this one is hydrogen, and the emission of hydrogen is just like 1, 2, 3, 4 wavelength. For helium, also we have 1, 2, 3, 4, 5 different wavelength instead of a continuous spectrum as with the white light. Also with neon, we have a lot of different spikes as wavelength. Okay, instead of a continuous one, each element has a specific, like this is like the digits in the fingers digit is the same for each element. Okay, so for hydrogen, this is always going to be the emission spectra. You're going to see 4 lines. For helium, this 5 lines, and for neon, all of this line. Okay, so the light emitted by hydrogen contains distinct wavelengths that are specific to hydrogen. So here we have again, this is the pink color for hydrogen, and you put it through the slit and the prism, and you're going to see the 4th line, and for the emission spectrum and the emission spectrum from hydrogen with 4 different wavelengths instead of the continuous wavelength as for the white light. Now, to try to explain this, there is a very interesting model. It's known as the Niels Bohr that was developed to trying to explain these results. So here in the middle, we have the nucleus. Inside the nucleus, as we mentioned before, we have the protons and the neutrons. And around the nucleus, we have different orbits. We have one orbit here. We have another one here. We have another orbit here. The N means orbit. This is the N4, or the orbit number 4, or orbit number 5. So this is the model that he established with the nucleus in the middle and orbits around them, around the nucleus, and they are pretty, like they have different distance. Okay, so the energy of each Bohr orbit specified by the quantum number n, 1, 2, 3, is fixed or quantized. Bohr orbits are like steps of a ladder, each at a specific distance from the nucleus and each at a specific energy. So here we have, for example, this is orbit number 1, orbit number 2, orbit number 3. Now, it is important that to go from 1 to 2, you need specific energy. You need to have a specific energy to reach to this point. If you have less than that energy, you can't reach this orbit. You will always be in number 1. So it is impossible for an electron to exist between orbits in the Bohr model. All the electrons are in each orbit, here in 1 or 2 or 3 or 4, 5, 6 in the orbit of that atom. So when a hydrogen atom absorbs energy, an electron is excited. Okay, so it means that that electron has more energy than it's supposed to have, okay? And that will make that electron to jump from the orbit number one, maybe to orbit two or three or four or five. It could be to any orbit if they have the specific energy to reach that orbit, okay? So the electron then relaxes back to the lower energy orbit, emitting a photon light. So once, for example, if this electrons reach for number, this one is number four, and then he came back to number three, he needs to release some energy, and that will be a light emission, okay, with a specific wavelength. So you excite the electron will jump to an orbit, and then it will come back. It could come back to the first orbit or to the second or the third, but it will reach a lower orbit from where it starts. Okay, so they will be in number one, will reach for, in this example, number three, and then it could come back to number two or number one. When it came back and relaxed, it will go to release an energy in form of light, and that light is a wave, and it has a specific wavelength. So those are the wavelength that we saw before in the spectrum of hydrogen or helium or neon. Okay, so that's why they have, in this case, for hydrogen. So hydrogen emission lines, since the amount of energy in a photon is directly related to its wavelength, the photon has a specific wavelength. The light emitted by excited atoms consists of specific lines at specific wavelengths, each corresponding to a specific transition between two orbitals. So for example, the line at 486 nanometers in the hydrogen emission spectrum correspond to an electron relaxing from the n equal to 4 orbit to the n equal to 2. So remember that the electron at the beginning, he was an n equals to 1. We excited that electron and it jumps from 1 to 4. And then it relaxed from 4 to 2. It released energy, and that energy corresponds to a wavelength of 486 nanometers. Also, there's another line in 657 nanometers. There's a longer wavelength and a lower energy. So because this is of lower energy, this corresponds to an electron relaxing from n equals to 3 to an orbit the n equals to 2, the same concept. In this case, this electron was at the beginning on 1. We excite that electron, it jumps to an n equals to 3, and then when it releases when it jumps to the second orbit, it releases energy because it needs to be relaxed, and it releases energy, and that energy corresponds to a wavelength of 657. The amount of energy from 3 to 2 is smaller than the energy released from an N4 to 2. That's why the wavelength is longer, okay? Because remember that as longer the wavelength, lower the energy, lower the frequency. So here we have an example. Here we have the red line that we saw before in 657 for hydrogen. So this is due to the transition from N3 to N1. Okay, remember, to N2. Remember that at the beginning the electron was in N number 1. It was excited to N number 3 in this specific sample, and then that electron that was excited in N number 3, it released energy to reach the N equals to number 2, and that energy was correspond to a wavelength of 657. There was the same electron could reach to the n equals to 4. When it reached the n equals to 4, and it wants to relax to n equals to 2, it releases an amount of energy, and that amount of energy is correspond to a wavelength of 486 nanometer. And this one from n equals to 5 to n equals to 2, this is going to have a larger energy. So because it has a larger energy, it has a smaller wavelength. Remember that smaller wavelength, higher the energy, higher the frequency. So from n equals to 5 to n equals to 2, it releases a lot of energy, and that energy corresponds to a wavelength of 408 and 34 nanometers. Okay, so remember, these are excited electrons. They were first in the n equals to 1, but when they were excited, some of them jumped to number 3, the orbit number 3, others to orbit number 4, and others to orbit number 5. And then they came back to the orbit number 2, and they released a specific amount of energy that correspond to those emission lines that we saw in the emission spectrum for hydrogen. Now, this model basically was very successful for to explain the lines predicted for the hydrogen emission spectrum. However, it failed to predict the emission spectra for other elements that contain more than one electron. For this and other reasons, the Bohr model was replaced with a more sophisticated model called the quantum mechanical or wave mechanical model. And we're going to see that in the next slides. So, the quantum mechanical model, this basically is a model with atoms and orbitals. The quantum mechanical model of the atom replaced the Bohr model in the early 20th century. In the quantum mechanical model, Bohr orbits are replaced with quantum mechanical orbitals. Basically are the same concept, but is from a different perspective, and we're going to explain that a little bit later. The orbitals are different from the orbits in that they represent probability maps that shows a statistical distribution of where the electron is likely to be found. So those are the orbital statistical distribution of where the electron is likely to be found. Quantum mechanics revolutionized physics and chemistry because in the quantum mechanical model, electrons do not behave like a particle flying through space. We cannot in general describe their exact path, the exact path of the electrons. So an orbital is a probability map that shows where the electron is likely to be found when the atom is probed. It does not represent the exact path that an electron takes as it travels through space. So, contrast the behavior of a baseball with that of an electron. Imagine a baseball thrown from the pitcher's mound to a catcher at home plate. The baseball's path can easily be traced as it travels from the pitcher to the catcher. As we can see here, we can draw the path of that ball as go from the pitcher to the catcher. In the quantum mechanical world of the electron, the catcher could not know exactly where the electron would cross the plate for any given throw. He would have no way of putting his mitt in the right place to catch it. However, if the catcher kept track of hundreds of electron throws, he could observe a reproducible statistical pattern of where the electron crosses the plate. He could even draw maps in the strike zone showing the probability of an electron crossing a certain area. These maps are called the probability maps. Okay, so they basically observe of how many times those electrons reach those specific areas, and they can create those probability maps. So for example, to describe the behavior of a pitch electron, you would have to construct a probability map of where it would cross a home plate. So most of the times the ball was hit in this place. There was a 40% around this, all of this place, and the 70% all around this, including the two middle areas. Okay, so 20% will reach here in the middle, 40% will reach the middle and also this area, and 70% will reach all this area, including those in the middle. So let's talk about the principal quantum numbers for orbitals. In the quantum mechanical models, a number and a letter specify an orbital or orbitals. The lowest energy orbital in the quantum mechanical model is called the 1s orbital. Every element has a 1s orbital. This is the lowest energy orbital in the quantum mechanical model. It's specified by the number 1 and the letter s. The number, we're going to talk a little bit first about the number, is called the principal quantum number n and specifies the principal shell of the orbital. So we have a 1, we can have 2, 3, 4, 5, 6 different n numbers. Okay, so that will be the principal quantum number. The single electron of an undisturbed hydrogen atom at room temperature is in the 1s orbital. This is called the ground state or lowest energy state of hydrogen atom. The absorption of energy by a hydrogen atom can cause the electron to jump, as we saw before when we tried to explain with the Bohr model that they jump to orbit 2, 3, 4, or 5. So in this model, it can jump from the 1s orbital to a higher energy orbital. When the electron is in a higher energy orbital, the hydrogen atom is said to be in an excited state. So when that electron, any electron, is in the lowest energy state, that state is called the ground atom. When an electron has a higher energy, is in a higher energy orbital, it's known as the excited state. All the atoms of each element have one ground state and many excited states. So energy increases with the principal quantum number. The higher the principal quantum number, the higher the energy of the orbital. So for n equals to 1, you have this energy. For n equals to 2, you have this energy. So for reach this n equals to 2, you need to add all of this energy. For n is equals to 4, you need to add all of this energy to reach this excited state if you start in n equals to 1. So the possible principal quantum numbers are 1, 2, and 3, with energy increasing as n increases. Since the 1s orbital has the lowest possible principal quantum number, it is in the lowest energy shell and has the lowest possible energy. So all the electrons in the 1s orbital, they have the lowest possible energy from all the other electrons of an atom. So let's talk about the shapes of the different quantum mechanical orbitals. The letter, we talk about the number, okay, and now we're going to talk about the letter. It indicates the subshell of the orbital and specifies its shapes. So each orbital may have different subshells, okay? The possible letters are S, P, D, and F, and each of them with different shape, okay? So we have 4 different subshells, the subshell S, the P, the D, and the F, and each of them has a specific shape, and we're going to discuss that a little bit later. The orbitals within the S subshells have a spherical shape. All the S subshells are has a spherical shape. So orbitals are sometimes represented by dots, where the dot density is proportional to the probability of finding the electrons. So for example, the dot density for the 1s orbital is greatest near the nucleus and decreases farther away from the nucleus. The electron is more likely to be found close to the nucleus than far away from it. Orbitals can be represented also as geometric shapes that encompass most of the volume where the electron is likely to be found. Remember that these are basically statistical probabilities, okay, of where you can find those electrons. The 1s orbital can be represented as a sphere that encompasses the volume within which the electron is found 90% of the time. If we superimpose the dot representation of the 1s orbital on the shape representation, we can see that most of the dots are within the sphere, meaning that the electron is most likely to be found within the sphere when it is in the 1s orbital. So let's see that. Dot density and shape representation of the 1s orbital. The dot density is proportional to the probability of finding the electron. So here we have a representation of a dot representation of where you can find that electron. As you can see here, it's the shape basically is like a sphere. The greater dot density near the middle represents the higher probability of finding the electron near the nucleus. This one is the shape representation, okay? This one is a dot, and this is the shape representation, that is a sphere for 1s, and this is the superimpose of both of them, and they basically are really accurate in that sense. So we have the dot representation and the sphere representation for the 1s subshell. So the number of subshells in a given principal shell is equal to the value of n. What that means? In shell number 1, we have one subshell. It's the S. So the only subshell you're going to find in the shell 1 is going to be the 1s. In shell 2, we're going to have 2 subshells. One is going to be an S, and the other subshell is going to be the P. So we're going to have a 2s and also a 2p. In the third shell, we're going to have 3 subshells, the 3s, the 3p, and also the 3d. And for the shell number 4, we're going to have 4 subshells, the 4s, the 4p, the 4d, and the 4f. So in shell number 1, The only one that we're going to find is 1s. There there is no existence of a 1p or 1d. Neither you're going to find a 2d or 2f. The only options that you have for shell number 2 is a 2s or a 2p. Okay, for n, 1s. You're going to find never 1p, 1d, or 1f. So the 2s orbital is similar to the 1s orbital but larger in size. So here we have an example of a 1s orbital, and the 2s, remember that the 2 is the number of the shell, the s is the represent the subshell. The subshell s, the form is a sphere, so in the 2s is going to be the same as the 1s but larger. Okay, so because it's an s subshell, the shape of the S is going to be always a sphere, okay? But in this case, it's going to be larger. For the 3S, it's going to be larger. It's going to be also a sphere, but larger than this one, okay? So the 2p orbitals. This figure shows both the dot representation in the left and the shape representation for each p orbital. So the p orbitals they are like dumbbells, okay? And as you can see here, you have in the x-axis, this is the probability to find the electron is going to be in the left and the right side. Here, okay, this is called a node, N-O-D-E, a node. In the node, the probability to find an electron is basically 0. Okay, so in this point here, in this node, the probability to find an electron is 0. You can find the electron around here or also around here, but here is basically 0. Okay, in the s orbital, it's a sphere. You don't have a node because it's a circle. You have all covered there. But in the p orbitals, you're always going to have one node here in the middle where the probability to find the electron is 0, while you can find the electron in this lobe or this lobe. So you're going to have a p orbital for each of the coordinates. This one is the px, this one is the py, and this one is the pz. Okay, so in the py, the same concept. You're going to have here the node, okay? This in the front part of your computer, this in the back part of your computer, and these are the probability region where you can find the electrons. And this one is the z, the pz, okay? So here, the same thing, you have a node here. The probability to find an electron there is 0. And in these 2 points, these 2 areas, is where you can have a higher probability to find the electrons. So orbitals when n is equal to 3. When n is equal to 3, we have 3 different subshells, that 3s, 3p, and 3d. So the next principal shell, n is equal to 3, contains the 3 subshells specified by s, p, and d. The s and p subshells contain the 3s and 3p orbitals, similar in shape to the 2s and 2p, but slightly larger. Okay, remember, as when you are in a larger shell, okay, the area is going to be larger than the one before, but slightly larger and higher in energy also. The d subshells contains 5 d orbitals. Now remember, the 1s or the s subshell is you're going to have just one type of s, 1s, 2s. The p, you're going to have 3 different p subshells, px, py, and pz. For the d, you're going to have 5 different orbitals, okay, in this subshell. So this one is like this. You have 4 different lobes, okay. You have the node in the middle and these 4 areas where you can find the electrons. This one is in this coordinates here, okay, in the plane. This one, so you have the same concept. You have the node here and 4 areas where you can have a higher probability to find the electrons. The number 3 is this one, basically in the z plane, okay, where you can have the 4 probabilities, higher probability to find the electrons, and in the middle of the node. This one is in the x, basically axis here, including the coordinates. So this one also you have the node in the middle and the 4 areas of higher probability to find the electrons. And this one, okay, also with this donut in the middle and a huge like p orbital, okay, in the z axis. So these are the 5 different shapes for the d subshells, okay, the d orbitals. Remember, you start to see this type of orbitals in shell number 3. You're not going to see this in shell 1, neither in shell 2, but you can find it in shell 3, 4, 5, or 6. You can have a 6d, okay? So, from orbits to orbitals, the quantum mechanical model predicts the bright line spectrum of hydrogen as well as the Bohr model does. The quantum mechanical model can predict the bright line spectra of other elements. The Bohr model cannot predict spectra for atoms with more than one electron. The Bohr model was replaced with a more sophisticated model called the quantum mechanical or the wave mechanical model. And the Bohr model is still important because it provides its logical foundation to the quantum mechanical model and reveals the historical development of scientific understanding. That's why we discuss a little bit about the Bohr model, even though in these days we are basically the discussion of those behavior of electrons is based on the quantum mechanical or wave mechanical model. So let's talk now about the electron configuration, how electrons occupy the orbitals, okay? What is the range of those electrons? An electron configuration shows the occupation of orbitals by electrons for a particular atom. Remember that each atom has a specific number of electrons. Hydrogen is number one, so it has one proton, one electron. Helium has two proton, two electrons, okay? So each atom has a specific number of electrons as an atom, so they also have a specific way that they arrange those electrons in the atoms. Two, the electron configuration for a ground state hydrogen atom is as follows. Is 1s1. Remember, the 1s is the lower orbital you can find with the lowest energy. And because you have just one electron, you use the representation 1s that represented the orbital, and you put like 1 as an exponent. That is the meaning of that you have just one electron in this orbital. So for hydrogen that has just one electron, it's 1s1. The electron configuration tells us that hydrogen's single electron is in the 1s orbital. Now, even though the hydrogen just has one electron, but it has also all the other orbitals. It has a 2s, it has a 2p, it has a 3s, 3p, 3d. It has all of them available, but just one electron. Okay, that's really important. So hydrogen has other orbitals, but they doesn't have any electrons. They just have one electron. So you put that electron in the lowest energy orbital. So in this case, it's a 1s. So that's why the electron configuration for hydrogen is 1s1. But remember that even though that is the 1s1, also you have available the 2s, the 2p, the 3s, the 3p, 3ds, and what all of them available for hydrogen. So electron configuration, we also have another representation that is called the orbital diagram. Another way to represent this one is using give basically the same information but shows the electron as arrows in a box representing the orbitals. The orbital diagram for a ground state hydrogen atom is as follows. So you have hydrogen, you have here a box, you have the 1s, you put a 1s, that's the orbital in the bottom, and then you put one arrow, okay, with half arrow basically that represent an electron. Okay, this arrow represents one electron. The box represents the 1s orbital, and the arrow within the box represents the electron in the 1s orbital. Also, we have another concept that is called the electron spin. In orbital diagrams, the direction of the arrow represents the electron spin, a fundamental property of electrons. The Pauli exclusion principle states that orbitals may hold no more than two electrons with opposing spins. Okay, so you can have just in one orbital two electrons, and they must have opposing spins. We symbolize this as two arrows pointing in opposite direction as this. Okay, so this, when you have to put two electrons in one box, you're going to put it like this. You can put both of them pointing to the top or pointing down. Okay, one must go pointing up and the other pointing down. Energy ordering of orbital for multi-electron atoms. So in multi-electron atoms, the subshells within a principal shell do not have the same energy because of electron-electron interactions. Different subshells within the same principal shell have also different energy. So that means that if for example, the orbital 2, you have the shell number 2, you have two subshells, 2s and 2p. Even though they are in the same shell, but the 2s has a different energy as a 2p. The 4s subshell is lower in energy than the 3d subshell, even though its principal quantum number is higher. So that means that it's not a specific order as 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 43, 4p, 4d. Okay, so it's not in that order. It has specific order, and we're gonna show that in a little bit while. So here we have basically the energy 1s. We have the 2s. The next in energy is the 2p. Then we have the next in energy 3s. Then the 3p, and we expect that it's gonna be the next one 3d, but the next one is 4s. Okay, so you go from 3p to fill the electrons, 3p to 4s, and then to 3d. And then from here, you go to 4p, and instead to go to 4d, you go to 5s. So this is a very tricky way that you need to know how to fill this electron. And to simplify this, we're gonna do an example a little bit later. I'm gonna show you a way that you maybe is gonna help you to understand and memorize how to do it. And actually, you're not gonna need to memorize. You can just you will come out with it with a simple way. I will show you in a little bit while. So let's write first the ground state for helium. The helium has 2 electrons. Okay, so once again, in each orbital we can put 2 electrons. So for helium, you're going to use the 1s, okay, 1s2. And here, okay, this is the configuration, electron configuration, 1s2, and the orbital diagram, 1s and 2 electrons. Remember that we need to put each half arrow pointing in opposite ways, okay? A lithium atom has 3 electrons. So now we have the 1s2, the 1s with 2 electrons that is filled, so we need to use the 2s1. The next one is a 2s1. So here we have the 1s2, 2s1, okay, as the electron configuration for lithium that has 3 electrons. The orbital diagram, it must be one box for 1s, which has 2 electrons, as here, okay, and then we have one more electron that we need to put in the 2s orbital, okay, and we can point it, most of the time, point it up, so you can put also point back, pointing down, it doesn't matter, but most of the time, the one that you put alone usually points up, okay. So for carbon, which has 6 electrons, the electron configuration and orbital diagram are as follow. So here we have 6. We have 2 in the 1s, 2 in the 2s, and 2 in the 2p. Okay. Now, the 2p electrons occupy the p orbitals singly rather than pairing in one orbital. If you have the chance to put them in individual orbitals, okay, remember that the 2p, as we saw before, we have a p orbital in each of the 3 axes, okay, the 3p, 3px, 3py, and 3pz. That's why we have 3 different here, three subshells of p, okay. For s, we just have 1. For p, we have 3, and for d, we have 5, okay. So that's why we have 3 boxes here, okay, 1 for each of the axes, okay, px, py, pc, doesn't matter which one is 1, but each one represents one of them. Now, the important thing is that we have 3 spaces available, okay, when we can put at least 2 electrons each of them. But the thing is that as we are filling them, we're going to put 1 first in each one individually, okay? If we don't have any other option, then we start to pair them, okay? But as long as we have another option to put another electron, we're going to put it alone by itself. This is called the Hund's rule. When filling orbitals of equal energy, electrons fill them singly first with parallel spins, okay? So we just forget about this one because we just filled this before as 1s2 and 2s1. We have 4 electrons. Carbon has 6, so we need to use 2 of these spaces here to put the electrons. As I mentioned before, most of the time we pointed up these electrons that have these half arrows. So this is the way that we can use to write the order, okay? So we can draw like a ladder 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5f, 6s, 6p, 6d, 7s, and then start to draw an arrow from the top to the bottom, diagonal like this, okay, from the right side to the left side. And then we can start from 1s going down and then going up here, 2s going down and then going up here, to p3s. So 1s, 2s, 2p, 3s. Then 3p, 4s, 3p, 4s. Then from the 4s, you go up here, 3d, 4p, 5s, 3d, 4p, 5s. And then from this arrow, you go back to this one and goes to 4d, 5p, 6s, 4d, 5p, 6s. This is the order, the right order to fill the electrons. Okay, so this is this one. You don't need to learn it. If you just write this 1s, 2s, 2p, 3s, 3p, this is basically logical. Remember that in shell number 1, you just have just one subshell, the 1s. Shell number 2, 2s, 2p. Shell number 3, 3s, 3p, 3d. 4, 4s, 4p, 4d, 4f. 5, 5s, 5p, 5d, 5f. And subsequently, okay? So, and then from right to left, right to left, right to left on top of each of them, and then try to join them, okay, with this way, 1s, 2s, going down, going up here to p, 3s, 3p, 4s, then 3d, 4p, 5s, then go up 4d, 5p, and this will give you this order. That is the one that you need to use, okay, to create the electron configuration and also the orbital diagram. So to write electron configuration, the lower energy orbitals fill before higher energy orbital. Always, you start with the 1s, then the 2s, 2p, etc., etc. Orbitals can hold no more than 2 electrons each. When 2 electrons occupy the same orbital, remember they must have opposite spins, one pointing to the up and one pointing down. Most of the time we use the half arrow. This is known as the Pauli exclusion principle. And when orbitals of identical energy are available, as for example, the p orbitals that we have 3 or the d that we have 5, all of these are first occupied singly by electrons with parallel spins rather than electrons in pairs. This is known as the Hund's rule. Once you have one in each of the orbital, then the next one you start to pair, okay? So the electron configuration of neon represent the complete filling of N equals to 2 principal shell. So here we have nitrogen. Nitrogen has 7 electrons, so that's why it's a 1. We have electron configuration of 1s2, 2s2, 2p3, 3, 4, 5, 6, 7 electrons. And the diagram is going to be 1s with 2 electrons, 2s with 2 electrons, and the p is going to be 1 electron in each of them. Okay, remember that we have 3 spaces available, but we can put 2 here and 1 here. Okay, we need to put 1 individually first, and then we're going to start to pair them, as for example with oxygen. With oxygen we have 8 electrons, so it's basically 1s2, 2s2, 2p4. So 1s2, 2s2, and the 2p4. Now in this one we're going to have other option that to put this electron with this first one. So we have a pair of electron in this subshell. Okay, for fluorine with 9, we have 1s2, 2s2, 2p5. So 1s2, 2s2, and 2p5. We have 5 electrons. And the last one, that is neon. This one must be, in this one, we're going to have 2 electrons here. So 1s2, 2s2, and 2p6. Okay, so neon complete all this shell here in number 2. You don't have any more space to put another electron in this shell number 2. So the noble gas core notation, when writing electron configuration for elements beyond neon or beyond any other noble gas, the electron configuration of previous noble gas can be abbreviated by the symbol for the noble gas in brackets. So for example, sodium. Sodium is the element that goes after helium. Okay, so, and it has 11 electrons. So the electronic configuration must be 1s2, 2s2, 2p6, and 3s1. So we have 2 and 2, we have 4, plus 6, we have 10, plus 1, we have 11 electron. And this order is the same as we saw before, okay, with the ladder. There's where it comes that order. So the thing is that this configuration here, this part of the configuration is similar of neon, that is a noble gas. So we can abbreviate this electronic configuration by saying that the electronic configuration of sodium is neon in bracket and 3s1, because this from here to here represent the configuration of neon, and we add this to represent that here we're talking about the electronic configuration of sodium. Okay, so this is how to use the abbreviation using the noble gas core notation. So electronic configuration and the periodic table. Valence electrons. The valence electrons are the electrons in the outermost principal shell. The principal shell with the highest principal quantum number n, where we can find electrons. Okay, so these electrons are important because they are involved in chemical bonding. The valence electrons are the electrons that will be involved in chemical reactions always. Okay, so that's why these valence electrons are really important. They are found in the outermost principal shell, so they are the electrons that are most exposed in an atom. So it's basically why they are more reactive, and they are part of the reaction because they are the most available to be part of a chemical reaction. Electrons that are not in the outermost principal shell are called the core electrons. Silicon has 4 valence electrons, those in the n equals 3 principal shell, and 10 core electrons. So this is the electronic configuration for silicon. Okay, 1s2, 2s2, 2p6, 3s2, 3p2. So the outermost shell is shell number 3. So that means that all the electrons in shell number 3, all of them, including the s and the p, all of these 4 electrons are valence electrons. The other ones are the core electrons. For selenium has 6 valence electrons, and this one is really tricky, okay, because the 4s, when we start to put electrons, we need to fill first the 4s before the 3d10, okay, as the order that we saw before in a few slides before. So even though we put them in this order, but we need to remember that this one is part of the shell number 4, both of them. So in the outermost shell, we don't have 4, we have 6 electrons. Okay, so we have 6 valence electrons for selenium, and all the others are the core electrons. Okay, so in the physical way, this 4 electrons and these 2 electrons, they are in the outermost shell. Okay, that is number 4. That's why we have 6 valence electrons, this 4 and this 2, even though these 2 are filled before the 3d10. Okay, but this is still part of the 4 shell, that is the outermost shell in the atom in this case. So electron configurations and the periodic table, the elements within a column of the periodic table all have the same number of valence electrons and similar outer electron configurations. So as we can see here, for family 1, we have the hydrogen 1s1, lithium 2s1, sodium 3s1. So they basically have the same outer electronic configuration, s1, s1, s1. Even though they have a different shell, they are in shell 1 and shell 2 and shell 3. For the family number 2, we have a 2s2 and 3s2. For family number 3, we have 3a, 2s2, 2p1, 3s2, 3p1. For 4, 2s2, 2p2, 3s2, 3p4. We can see that for family 1, we have just 1 valence electron. For family 2, 2 valence electron. For family 3, we have 2 and 1, 3 valence electron. For family 6, we have 4 and 2, 6 valence electron. And for 8, we have, in this case, neon, 6 and 2, 8. Why helium is part of the noble gas? Because helium has the most number of electron that can be put in the outermost shell, that is 1. Okay, in the case of helium, the outermost shell is just 1, so that's why, and helium has filled those spaces with the 2 electrons, so that's why it's part of a noble gas, and it's the one that only that it don't complete the that rule that is called basically the octet rule, because we have 8 electron. Helium doesn't obey that law, but it's part of the noble gas because it fills all the electrons, a space of electrons available for each shell. And pattern exists for the entire periodic table. The first two columns on the left side of the periodic table are the S block. The 6 columns in the right side of the periodic tables are the P block. The transition metals are the D block, and the lanthanides and actinides, also called the inner transition metals, are the F block. So here we have basically that, what we mentioned before. All of these are the S block. As you can see here, the only in the valence shells, basically, you're going to find just the S orbital. So that's why these are the S block. Here, you're going to find S and P. So these are the P blocks. Here, you're going to find the Ds. Okay, so these are the D block. And here, you're going to find the F. Okay, in each of the configuration, you're going to find an F orbital. So you're going to have all these are known as the F block elements. So these are the S block, the D blocks, the P block, and the F block, okay, for the periodic table. Periodic trends in electronic configuration of the main group elements. The number of valence electrons for any main group element is equal to the group number of its column. Helium is an exception, and we talked a little bit about that before. So chlorine has 7 valence electrons because it is in the column with group number 7A. Okay, so chlorine has 7 valence electrons because it's part of the group number 7A, the family 7. The row number in the periodic table shell in the periodic table is equal to the number of the highest principal shell. Okay, chlorine is in row 3. It's the highest principal shell is the n equals to 3 shell. Remember that the main group elements are those in the 2 far left columns, 1A, 2A, and the 6 far right columns, 3A to 8A of the periodic table. The periodic trends in the electronic configuration of the transition series elements. So, the transition metals have electron configuration with trends that differ somewhat from main group elements. The principal quantum number of the d orbitals being filled across each row in the transition series is equal to the row number minus 1. For the first transition series, the other configuration is 4s2 3d. So here we can see that instead, even though they are in the 4 lane, but the d is going to be 1 minus that number. So that's why you're going to find the 4sd and the 3dx, where x is going to be the electrons that are in that d orbital. 2 exceptions: chromine is 4s1 and 3d5, and copper is 4s1 and 3d10 instead of 4s2 and 3d9. Okay, is 4s1 and 3d10, but it's the same concept. You're going to see the 4s and the 3d instead of the 4s and the 4d. These exceptions occur because of how filled D subshell and a completely filled D subshell are particularly stable. Okay, so that's why instead of to see the 4s2, 3d4, it's better to have this orbitals half filled. Okay, so you use one of these electrons and put it here. As the same way here, copper is when you fill them, you see that it's going to be 4s2, 3d9, but you must fill this first. So you put one of this electron here, and you will fill this with a 3d10 4s1. So that's particles stable. That's why these are 2 exceptions: the chromine and the copper. So the periodic trends in electronic configuration of transition series element. The number of the outer shell electrons in a transition series does not change as you move across the period. The transition series represent the filling of core orbitals, and the number of outer shells electron is mostly constant, either 2 or 1. 2 electrons for 4s2 3dx, 1 for the 4s1 3d5, or for the 4s1 3d10. So let's write the electron configuration based on the position in the periodic table for phosphorus. Okay, so here we have phosphorus. Okay, and phosphorus is in the line number 3. Okay, period number 3. So, and also before phosphorus we have the neon. So this is the inner electron configuration, neon. We can use that configuration first, okay? And then we are at 3, so it's going to be 3s2 because we have 3s2 here. And then the next one's going to be 3p1, 3p2, 3p3. And that's the configuration, okay? So we just put the noble gas configuration that is before the element that you're looking for, and then you look for the period here, number 3, and you can go from 3s2 and then 3p1, 3p2, 3p3, okay? The same thing is going to happen with this other. Remember that in this case, we're going to have the 4s1, 4s2, but this one is 3d1, okay? 3d2, 3d3. Remember that this one is going to have the period minus 1 as the principal number, okay, for the d. So this is going to be 4s, 3d, and 4p, okay? But this one is going to be the same as the s. So it's going to be 4s, 3d for all of this, and this one is going to be 4p, the same one here. 5s, these are going to be 4p, 4d, all of this, and this 5p. So write the electron configuration by seeing the position of the periodic table. The inner electron configuration is the electron configuration of the noble gas that immediately precedes that element in the periodic table, and represent the inner configuration with the symbol of the noble gas in brackets. Okay, so you need to put them in brackets. And the other electrons can be determined from the element's position within a particular block, the S, the P, the D, or the F in the periodic table. Trace the elements between the preceding noble gas and the element of interest and assign electrons to the appropriate orbitals, as I mentioned before. The highest principal quantum number is the highest n value is equal to the row number of the element in the periodic table. Okay, so we saw in the one before, for phosphorus, is going to be the 3. Okay, so that's the highest n value. For any element containing the electrons, the principal quantum number and value of the outermost d electron is equal to the row number of the element minus 1. Okay, so that's why when we reach the 4 period, we're going to have 4s and 3d instead of 4d. Okay, because we're going to subtract 1, okay, from the row number. So some observations. Sodium tends to form sodium positive ions. Those are called cations. And fluorine tends to form F minus ions called anions. Can we explain that with the quantum mechanical model? Why for sodium is easy to release that electron as a fluorine to obtain an electron as an ion. They are positive in the case of sodium and negative and anions in the case of fluorine. Some elements are metals and others are nonmetals. And the noble gases are chemically inert and the alkali metals are chemically reactive. Can we explain these things by using the quantum mechanical model? Let's see. The chemical properties of elements are largely determined by the number of valence electrons they contain. Their properties vary in a periodic fashion because the number of valence electrons is periodic. So here we have the noble gases. Calculations shows that atoms with 8 valence electrons are predicted to be particularly low in energy and therefore stable. This is a rule that is known as the octet rule. Okay, the octet rule, because they have 8 electrons. They have the fill or the subshells of each of the shells. Okay, there's S and the P. We have 8 electrons, 8 electrons, 8 electrons. All of the other elements want to have this same configuration. The noble gases are chemically stable and thus relatively inert or non-reactive as accounted for by the quantum model. So that's why you're going to find argon as Ar. You're not going to find argon as a molecule of Ar2 because they are stable. They don't need any more electrons. The same way for helium, for neon. They are just atoms, very stable. They are not be combined with other molecules themselves. Elements with electrons configuration close to noble gases are the most reactive because they can't attain noble gas electrons configuration by losing or gaining a small numbers of electrons. So the alkali metals. The alkali metals, group 1, are among the most reactive metals since the outer electrons configuration N is S1 is one electron beyond a noble gas configuration. So if they get rid of this electron, they will have the same electron configuration of the noble gas that precede them. So if they can react to lose the electron, they attain a noble gas configuration. This explains why the group 1 metals tend to form a plus 1 plus cation. So that's why, because they lose one electron, the electron, remember, has a negative charge. So as an atom, they are neutral. So if you're losing a negative charge, you're going to produce a positive charge. That's why lithium, sodium, potassium, beryllium, cesium, all of them are, as an ion, are 1 plus. Sodium 1 plus, potassium 1 plus. The alkaline earth metal is basically the same concept. They have in their outermost shell a configuration of Ns2, okay? So you have 2 electrons, and if they get rid of those 2 electrons, they will have the similar electronic configuration of a noble gas. So in their reaction, they tend to lose 2 electrons, and because they lose 2 negative charge, now they will form an ion with a 2 positive charge, a cation with a positive 2 charge. That's why calcium, magnesium, beryllium, strontium, all of them has a 2 positive charge. Now for the halogens, the group 7 all have Ns2 and Np5 electron configuration, as we can see here, S2p5, S2p5. The only thing that they need is to gain 1 electron, and they will have the same electron configuration as the next element that is a noble gas. Okay, so fluorine, chlorine just need one to be as the same as the other gas noble that is in the right hand. So that's why most of them, because they gain 1 electron, okay, and they have, and when they gain an electron, they will produce an ion with the same number of electrons as the noble gas. So that's why the 7 group, the halogens, are always -1. Fluorine -1, chlorine -1, bromine -1 as an ion. Okay, as an atom, they are neutral. They don't have charge as an atom. But when they are really reactive, because when they gain 1 electron, they're going to have the same electron configuration of a noble gas. So family 1 plus 1, family 2 plus 2, okay, for them it's really easy to get rid of 1 electron, okay, to have the same configuration of the noble gas before them, okay. And for this atoms, okay, when they are atoms, for them it's really easy to gain electrons, so they can produce these ions, and the electronic configuration of them, this, and this, all of them are the same as this noble gas that is neon. Okay, so as an ion, the N-3, the O-2, and the F-1, all of them has the same configuration as neon. The same thing with this 2 and this 2 and this 2. Okay. So let's talk about the atomic size, and we have 2 factors here. Okay, so number 1, as you move to the right across a period in the periodic table, the atomic size decreases. Okay, the atomic size decreases. The atomic size of an atom is determined by the distance between the outermost electrons and the nucleus. The size of an orbital depends on the principal quantum number. With each step across the period, the number of protons in the nucleus is increasing. Because you are increasing that positive charge, you will pull more those electrons, okay? This increase in the numbers of protons results in a greater pull on the electrons from the nucleus, causing the atomic size to decrease across the period. Number 2, as you move down a column in the periodic table, the atomic size increases. As you move down a column in the periodic table, the highest principal quantum number n increases. And remember, when we talk about the subshells, the shells, the 1s is smaller than the 2s because the 2s is larger. So as you go down, the number increase as well as the size. So since the size of an orbital increases with increasing principal quantum number, the electrons that occupy the outermost orbitals are farther from the nucleus as you move down a column, and that will not affect the size of the atoms. So here we have basically a graphic where we can see that the size of the atom will decrease from left to right because you're increasing the number of protons in the same shell, okay, number shell, and that's why the nucleus will pull more those electrons in the outer shell, and that's why they decrease the atomic size. While when you go down, okay, it tends to increase because you're increasing the shell number 1, 2, 3, 4, 5, 6, and that's why the orbitals are bigger or larger. So that's why the atomic size increase from the top to bottom and decrease from left to right. We also have ionization energy, and the ionization energy is the energy that you need to remove an electron. Okay, so ionization energy increases as you move to the right across a period and decreases as you move down a column in the periodic table. Remember that for the left side, it's easy to remove an electron, but in the right side, you need to gain electrons. So if they love to gain electron, it will be harder to remove that any electron. So that's why the energy of ionization increase, because the energy of ionization is the energy required to remove an electron. Okay, and it will decrease down because remember that when you go down a periodic table, the atom is larger, so the electron is going to be farther from the nucleus as you go down, so it's going to be more easy. So for the ones that at the top, you're going to need more energy than from the one in the bottom. So here the ionization energy increased to the right. Remember, for this one, it's really easy to remove an electron because as you remove electrons, you're going to have the same configuration as the electronic configuration of the noble gas before them. But for this one, most of the time they need to gain. So it's going to be difficult to remove an electron. So that's why the energy of ionization increased from left to right. And from the top to the bottom is more easy to remove this electron because they are pretty far away from the nucleus as compared to this one. So that's why you need more energy to remove electron from this one as from this one. The metallic property and the character in the periodic table, the metals tends to lose electrons in their chemical reaction, while the nonmetals tend to gain electrons. As you move across the period in the periodic table, ionization energy increases, which means that electrons are less likely to be lost in chemical reaction. So the metallic character decreases as you move to the right across a period and increases as you move down a column in the periodic table. So the metallic trends for the right will decrease, from the top to bottom will increase. Okay, the metallic character. So let's do a review of chapter 9. Light is a form of electromagnetic radiation, exhibits both wave-like and particle-like behavior. Particles of light are called photons. The Bohr models, the emission spectrum of hydrogen can be explained by Bohr model for the hydrogen atom. Each orbit is specified by a quantum number n, which also specifies the orbit's energy. The quantum mechanical model describes electrons' orbital, which are electron probability maps that shows the relative probability of finding an electron in various places surrounding the atomic nucleus. An electron configuration indicates which orbitals are occupied for a particular atom. Orbitals are filled in order of increasing energy and obey the Pauli exclusion principle. Each orbital can hold a maximum of 2 electrons with opposite opposite spins, and the Hund's rule, electrons occupy orbitals of identical energy single before pairing. The periodic table, elements within the same column of the periodic table have similar order electron configuration and the same number of valence electrons, and therefore have similar chemical properties. The periodic table is divisible into blocks, the S block, the P block, the D block, and the F block, in which particular sublevels are filled. As you move across the period to the right in the periodic table, atomic size decreases, ionization energy increases, and the metallic character decreases. As you move down a column in the periodic table, atomic size increases, ionization energy decreases, and metallic character increases. So this is the end of the model number 2 for chapter 9, electrons in atoms and the periodic table.